Hello students, welcome to standard 9 subject mathematics chapter number 9 areas of parallelograms and triangles. In this lecture number 2 in this lecture we will see the parallelograms on the same base and between the same parallels. In last lecture, very first lecture, we have seen some figures in which the two figures were on the same base and between the same parallels. They were different type of figures, but here we are going to talk about particularly parallelograms. If two parallelograms having on the same base and between the same parallels, what happens, that we will see. So related to that, the theorem 9.1 is parallelograms on the same base and between the same parallels are equal in area. This is the theorem 9.1 is. If we have the parallelograms with the same base and between the two parallels, they will have equal area, that is the theorem. So here, this type of situation is given. Two parallelograms are given, A, B, C, D, and the second parallelogram is given A, E, F, C, D, in which you can see BC is same base for both the parallelograms, means having the same base, and both the parallelograms in between the two same parallels as AF parallel DC, between that two parallels. So the data is here, we will write for two parallelograms A, B, C, D and E, F, C, D are on the same base and same base DC, and between the same parallels, that is AF parallel DC or DC parallel AF. These two parallelograms are. To prove, we want to prove that this type of two parallelograms which are on the same base and between the same parallels are having equal area. So that is here to prove parallelogram area ABCD is in notations we can write area of ABCD equals to area of AFCD, the next parallelogram. To prove this, we start with these triangles. One triangle is ADE on this corner. On this corner, the triangle BCF. In triangle ADE and triangle BCF, we start with which things are equal, that we will list here. So first of all, we can say the angle DAE, this angle, equals angle CBF, this angle. This and this angles we are showing equal. On which basis it is, you can understand here. The reason we heard that. The reason are they are corresponding angles from AD parallel BC. AD parallel BC is there because ABCD's parallelogram opposite sides are parallel. If AD and BC are parallel and AF is transversal, these angles are called corresponding angles from AD parallel BC and AF is transversal. So these two are corresponding angles, and because they are formed between the two parallel lines, that is AD parallel BC, so these corresponding angles are equal. We can show angle DAE equals to angle CEF. This is the reason. Say this result as number 1, result 1. Similarly, on this side now, angle AED. Now, this angle AED and angle BFC, this angle, are equal. Again, the same reason, corresponding angles, but this time the parallel lines are of the parallelogram EFCD, you know, DE parallel FC, DE parallel CF, and AF is transversal. So that is DE parallel FC. Between that two, these two angles are corresponding angles, and between the two parallel lines, the corresponding angles are equal with the transversal AF. So say result 2. Now the third angle in this triangle is, we have shown angle DAE equals to angle CBF in these two triangles. And next, second triangle also, angle AED and angle BFC we have shown equal. So what about the third triangle? If two angles of the two triangles are equal, then the third angle will be automatically equal because of angle sum property we know of the triangle. the sum of all three angles is 180. If two angles we have shown equal, the third will be automatically equal. So about the third angle, this angle is remaining in triangle. With the name angle ABE. This angle is equals to the third angle of this triangle also, that is BCF. The reason is, as we have shown two angles of the two triangles are equal, the third angle will also be equal, because angles are property of a triangle, and say this result as result number 3. So three angles of these two triangles, all the three corresponding angles we have shown equal. Also, one more thing, AD equals to BC. AD equals to BC. Why? Because opposite sides of parallelogram ABCD are equal. You know, ABCD is parallelogram and its AD and BC are opposite sides. So in parallelogram, opposite sides are equal. So AD equals to BC, we can write say result 4. Therefore, triangle ADE and triangle BCF, which we have started with, they are congruent. The reason is because of angle side angle using 1, 3 and 4. In 1, this angle we have shown equal A and B. In 3, this D angle and C angle we have shown equal in these two triangles. A and B equal, B and C equals, and between that two, the side AD equals to BC, that also we have shown. So this is what happening, angle side angle, and here also angle side angle. By ASA, both the triangles, triangle ADE and triangle BCF are congruent by ASA using 1, 3, 4. And now in this chapter, the beginning of the chapter, like lecture number 1, we have seen that if two figures are congruent, in last lecture, if two figures are congruent, they are having equal area. Here we have proved that triangle ADE and triangle BCF, two triangles are congruent. So they are congruent figures, congruent triangles, so they will have equal area. Therefore, area of ADE equals to area of BCF because of congruent figures they are. So this result 5 number. 5 number result it is we got. Now what we want to prove is area of ABCD equals to area of BFCD. So its left side we start. Area of ABCD equals, from the figure you can see, ABCD's area is composed of two areas. One of this triangle comes in that ADE. So that is area of ADE, triangle ADE, and this quadrilateral comes in that EBCD, area of EBCD. This quadrilateral and this triangle makes ABCD. So sum of these two we have shown, because non-overlapping figures, that is also in the last lecture we have seen, the area of whole figure, if it is composed of two non-overlapping figures, it will be equals to the sum of that two. So this way we have written. Now area of ABE can be written as area of BCF also, from result number 5 is, plus area of EDCB as it is. Now this situation you see in the figure, area of BCF means this triangle comes in that, plus area of EDCB, this quadrilateral comes in that. Sum of these two, what happens? Sum of these two, what it gives? It gives EFCD, the whole gives. So in place of this sum, you can write area of EFCD. So what we have started with here on the left side is area of EBCD equals to what we are getting, area of EFCD, that we wanted to prove. And that we have proved that parallelograms between the same parallels and having the same base, on the same base they have equal area. That way theorem 9.1 we have proved here. This theorem is very, very important for the exam point of view also. It can be asked of 3 or 4 marks. So this way we have to go and we have to prove this theorem. So based on this theorem 9.1, now we have the example number 1 that we will see. In figure, this figure is given. ABCD parallelogram given, ABCD you can see parallelogram given, and EFCD is a rectangle. You can see EFCD is a rectangle given. Also AL perpendicular DC given. This AL is on DC perpendicular given. We have to prove that number 1, area of ABCD, this parallelogram, equals to area of this EFCD, this rectangle. And second number we want to do that area of ABCD, the parallelogram, equals to BC into air, that is base into altitude. We want to do. So the solution number 1, first we want to do this ABCD equals to EFCD. You know that as a rectangle is also a parallelogram. By the definition of rectangle, you know, every rectangle is a parallelogram. So this rectangle EFCD is also a parallelogram, as well as ABCD is also given the parallelogram. So both are parallelograms. These both are parallelograms with same base on the same base DC. They are on the same base DC, and between the two parallels EB parallel DC also. So from theorem 9.1 we can use here both the parallelograms will have same area. That's here we have written directly area of ABCD, one of the parallelogram, equals to area of EFCD, the other parallelogram. Because why we have shown they are equal area? Because they are on the same base DC and between the same parallels EB parallel DC from theorem 9.1. So just only in one line we have proved that first one is ABCD, area of ABCD equals to area of EFCD. Now next to prove area of ABCD equals to DC into air, for that the second number, you know that area of rectangle equals to length into breadth. This is the formula, you know. So our area of ABCD, here we have proved in first that area of ABCD equals to area of EFCD, and EFCD is a rectangle. So EFCD is rectangle, so its length, if I consider DC as, into its breadth will be FC. So length into breadth, say result 1. Also, as AL perpendicular on DC given, AL perpendicular on DC given, here the 90 degree will be. So this AL and FC is also 90 degree on DC. So this AFCL is also a rectangle, we will say. If AFCD is rectangle, AFCL will also be rectangle because it is 90 degree making one of the angle of parallelogram. So it will be rectangle. Therefore, its opposite sides are equal. AL equals to FC we can write. Say result 2. Now from 1 and 2, in 1 what we have? Area of ABCD equals to DC into FC. So now we can write DC into FC. In place of that we can write AL from 2. So area of ABCD equals to DC into AL, that we do here, the second also. So this way, in this lecture we have seen the parallelograms on the same base and between the same parallels have same area as theorem 9.1. We have proved it, very important theorem. We have to write it 2-3 times and prepare it well for the exam point of view. It is very important. And based on this theorem, example 1 also we have seen and proved whatever was asked. Next examples and exercise 9.2 we